So last lecture, we were talking about the second price sealbed auction. We did find the best response. Well, we simplified things. We said, let's concentrate on the case with two agents. And we said, let's study the best response correspondence of agent one. Because if we know that, if we can find the best response of an agent, we can easily find strictly dominant and dominant strategies of the agent. So last lecture, we found that the best response correspondence of agent one, which was a function, because we assumed that there was only two players, which was a function of the bid of player two. We defined it as, we found it as the following. So if the maximum, I'll just write it shortly. Did we do it for two player or n player? I forgot for a minute. N player, so it was not two, so it's -1. The maximum bid made by all the other agents was less than V1. Again, we don't have to draw the graph. Actually, it's very intuitive. So the amount that the amount that player one will have to pay is less than the value of the object for him. So if he wins the auction, so he would like to win the auction. And in order to win the auction, he should bid the maximum of the bids of the maximum of the bids of the other agents or anything larger. So the best response correspondence in this case was maximum be -1 to infinity. If we had equality, then if he wins the auction, his net gain, he will get the object, which is like earning V1 liras. He will have to pay V1 because that's the maximum bid made by the other agent. So his net gain is equal to 0, which is also the net gain if he doesn't win the auction. So it doesn't really matter if he wins the auction or not. So he can bid actually anything. Okay. And if the maximum was greater than V1, then if he wins the auction, the amount that he has to pay is going to be more than the maximum, more than the value of the object for him. So in that case, he would not like to win the auction because in that case, his net gain is going to be negative, whereas if he doesn't win the auction, his net gain is going to be 0. So in that case, in order to lose the auction, he will have to bid an amount less than the maximum bid of all the other agents. So that's what we had, okay? So actually, last lecture, we kind of fast, without going into detail, we kind of illustrated this, that this is equal to V1. That's what we went over fast. Now what I would like to do is use a graphical method to illustrate this, okay? So we need a method. Graphs, pictures are very, very powerful tools. So in anything you study, whether it's mathematics, economics, history, using pictures is always a good idea. So try to make use of pictures. So that's what I'm going to try to do. So I'm not that bad with drawing two-dimensional pictures. With three-dimension, I have a big problem. My PhD supervisor, William Thompson, does those very nicely. And about three, that's impossible for me. I'll show you how William does it when times come. So what I'm going to do is, well, I'll use this axis for the strategy of player one. Now, we have several agents. So actually, I need B2. Well, I'll show you how William does this. B2, B3, B4, B5, and so on. Of course, it's very hard to draw a picture with 5 or more dimensions. But when I look at this, what I realize is that the best response correspondence, the best response of player 1 does not in particular depend on the bid of each and every agent. It only depends on the maximum bid made by all the other agents. Okay? So, but to start with, let's take it simple. Let's assume that there's only one agent. So B minus 1 is equal to B2. Okay? So the way I'm going to do it is if I mark a point here, B1 prime, B2 prime, this means that B1 prime is an element of best response of agent 1 to B2. Okay? That's not, if a point is marked, then the horizontal component of that point, B1 prime, would be we will interpret it as the horizontal component of that point, B1 prime, is an element of the best response of agent 1 to the vertical component, which is B2 prime. Okay? So that's how we're going to do it. Now, let's take that with that in mind. If a point is not marked, then it means that B1 prime is not a best response to B2 prime. Okay? So I need a point B1. I'll put it here. Okay? So if B2 is less than B1, then anything bigger than or equal to B2 is a best response of player 1. So if I take, for example, B2 prime here, then I need to find the corresponding point here. So let me draw the 45-degree line. So all these strategies of player 1 is a best response to B2 prime. Okay? So I will mark all these points. Okay? So if I take another point, B2 double prime, B2 double prime, all the strategies of player 1 greater or equal to B2 double prime is a best response of player 1 to the strategy B2 double prime of agent 2. So I'll mark all these points. So if I keep doing that, I will get, well, essentially I will shade all this region. All that region will be shaded, will be marked. When B2 is equal to B1, then anything is a best response, which means that this whole region should be marked. If B2 is bigger than B1, then any strategy from 0 to B2, B2 excluded, is a best response. So if I take, for example, B2 triple prime, B2 triple prime, any strategy in this region is a best response. So I'll mark all these points but exclude this point. And if I keep doing that, what I will get is, okay, I will get this. So that's the picture of the best response correspondence of player 1. Okay? They give the same information. Okay? These points included. These points excluded. Okay? So far, so good? So far, so good? Okay. Now let's go back to the case where there is more than one agent. As I said before, when I look at this, all I see is that the best response of player 1 depends on not the individual strategies of the players, but the maximum of those. So actually, if I had here on this axis maximum bid made by the other agents, I will get the same picture. Okay? So looking at this picture, How do I decide that this is the case? Well, what I do is take a strategy of player one. Take the strategy, okay? So let me erase these, okay? So is this in the intersection? Well, I draw a vertical line from this point, okay? So this point, B1 prime, is the best response for all strategies of player 2 in this region, and is also a best response to all strategies of player 2 greater than or equal to B1, but it's not a best response to these strategies of the other players, okay? Which means that it's not in the intersection because it's not a best response for some strategies of the other players, okay? The same thing is true for this. It's not a best response to some strategies of the other players. Draw that line. It's a best response to some strategies of the other players. It's a best response to some strategies of the other players, but it's not a best response to every strategy of the other players. So this strategy of player one is also not an intersection, okay? Now, this is the 45-degree line, so this is the point B1. So if I draw a vertical line from here, what do I see? It's always in the shaded region. So just looking at the picture, I can immediately conclude that the intersection of B1, the best responses of player one to strategies, profiles of the opponents, is equal to B1. So the picture is a very powerful tool. Just by looking at it, I can see what the intersection is. The intersection only contains V1. I'm done. Okay, that's it. Okay, rather than taking the intersection of all these infinitely many sets, just looking at the picture, I can conclude that. Okay, so far so good? So the key to find, if you're using a graphical method, what you have to do is for player one, you'll draw vertical lines. Okay, if the vertical line is always in the shaded region, that is the region which corresponds to the best responses, then it's in the intersection. Otherwise, it's not. Okay, that's it. Any questions? Any questions? What do I do for player two? Well, this time I will draw, actually, let's deal a little bit more with player one. Okay, so from here, we conclude that, we conclude two things. D1 star of gamma, for the second price seal bid auction, I'm going to use the symbol gamma, S for second, P for price, A for auction. Player one does not have a strictly dominant strategy in this game because, remember, for strict dominance, we need to have a single strategy which is always the only best response. That's not the case. Many strategies are best responses. And D1 of gamma SPA is equal to V1. By the way, this does not imply this. This picture implies this. Okay? Sorry? That's the symbol that I will use from now on whenever I'm talking about the second price seal bid auction game, the game which is the second price auction. Okay? So shorthand. Okay? Any questions? Any questions? Any questions? Sure. Strictly dominant strategy. So if you remember from our finding last lecture, I'll give you the theoretical. So a player had a strictly dominant, so SI star was a strictly dominant strategy of player I in the game gamma, if and only if, for any strategy profile of the opponents, the best response of player I to that strategy profile of the other agent was a single strategy, and it was always SI star. Okay? Whereas when I look So sometimes V1 is always a best response, but it's not the only best response. This strategy is also a best response to some strategies of the opponents. Okay? Okay? Yes, sir. Any questions?
Would it just be a vertical single line?
Exactly. So what would well, let's do some examples. So let's leave second price silver auction aside for a minute. Let me give you some games. For the sake of simplicity, let S1 be equal to the 0, 1 interval, and let S2 be also equal to it. Again, when I say they're equal, I don't mean, okay, we're abusing language here. Okay. So let me give you some examples and you let me know what the situation is. So the graph of B1 is of this form. What is your conclusion about D1 star gamma and D1 gamma? Sorry? There. The first one, D1 star gamma, empty. Right? Everybody agree? So when we look for every strategy of player 2, player 1 has a unique best response to every strategy. So for this strategy of player 2, this is the unique best response of player 1. For this strategy, this is the unique best response. For every strategy of player 2, there is a unique best response. There's a unique best response, but the best response keeps changing. Because of that, player 1, just by looking at this picture, we can conclude that player 1 does not have a strictly dominant strategy. Dominant strategy, again, it's empty. We check for the intersection. For the intersection to be non-empty, it means that player 1 should have a strategy which is always a best response. Well, this strategy is a best response to this strategy of player 2, but it's not a best response to this strategy of player 2. So this strategy is not always a best response. Actually, when we draw the vertical line, we see that any vertical line that we draw doesn't always lie in the graph of the best response correspondence. So the intersection is empty. So let's do one more. So, so this is the picture of B1. Strictly dominant strategies. Again, there is none. Right? You all see that? Just by looking at this. For example, for this strategy of player 2, player 1 has more than one best response. Hence, player 1 cannot have a strictly dominant strategy. Dominant strategy, which is 0.5. When we draw a vertical line from 0.5, we see that it's always lies in the best response graph. So it's an intersection. And actually, no other vertical line lies in the graph. So from this picture, we can immediately conclude that the intersection of the best responses of player 1 only contains 0.5. So 0.5 is a dominant strategy of player 1. Let's do 2 more, actually. Well, more than 2. So strictly dominant strategies. Again, none. Dominant strategies. So it's from empty set. Everybody agree? Everybody agree? No? Somebody doesn't, or? So that's from 0.5 to 1. Anybody else? None? You mean empty? Okay. So which one? How many vote for empty? How many vote for, well, quite a large group. Again, so from last lecture, again, we know that using best responses, we can find dominant strategies. So for dominant strategies, what we have to do is we have to look at the intersection. We have to look at this intersection. What is in that intersection? For this picture, anything from 0.5 to 1, right? So 0.5 is in the intersection, 0.64 is intersection, 1 is in the intersection. 0.2 is not, because it's not always a best response. So anything in this region. What was our theorem? Exactly. So first of all, without doing anything, your friend has a point, without doing anything, we should know that this can't be correct. Because if you remember, one of the first things that we discovered when we studied dominant strategy was that each player can have at most one dominant strategy. So just by that reason, this cannot be correct. But let's try to use our theorem. What did our theorem say? It said SI star was a dominant strategy if and only if the intersection contained the single element SI star. Here, the intersection contains more than one element. So this is false for any SI star. So this should be false for any SI star. Well, this will be false for any SI star if and only if it's empty. Okay, so far so good. But again, the thing to keep in mind, without, even if you didn't know the best response correspondences of player one, you should conclude that this can't be the case, because each player can have at most one dominant strategy. Okay? So for strict dominance, what should the best response correspondence look like? What should the best response correspondence look like? As one of your friends suggested somewhere over here. Okay. So it should be, the condition was, there should be a single best response to every strategy profile of the opponents, and it should always be the same. So if this is the case, then D1 star of gamma is equal to S1 star, which is also equal to the dominant strategy of the player. Okay? So for existence of a strictly dominant strategy, the best response correspondence should look like this. Okay? So far so good? By the way, on the same graph, I can plot the best response correspondence of player 2. This time, I will not change the axis. What I will do is, if a point is marked, it would mean that S2 is a best response of player 1 to S1. So this way I can both, for example, if I have a picture like this, so this is the graph of the best response correspondence of player 2. Let's say 0.7. What can I say about D2 star of gamma and D2 of gamma? Player 2 does not have a strictly dominant strategy. Why? Because it has, for some strategies of player 1, it has more than one best response. So that's empty. What about D2 star, D2 of gamma, dominant strategy of player 2? It's going to be 0.7. This time, to see whether a point is in the intersection of the best responses, we draw horizontal lines. This is not an intersection because it's never a best response. This strategy of player 2 is not in the intersection because even though it's a best response to all these strategies of player 1, it's not a best response to these strategies of player 1. So it's not in the intersection. So this time we draw horizontal lines. If the horizontal line always lies in the graph of B2, then it's an intersection. Okay? So very easy. Pictures are powerful tools. Any questions? Any questions? Okay. Well, let's go back to our second prize sale bid auction game. This time, let's take an arbitrary agent. Okay. So, well, actually, let me draw it from scratch. So, what would the graph of an arbitrary, no, it's not agent one, it's any agent. What would be the graph of the best response correspondence of player I look like? Well, if the maximum bid made by the other agents is less than BI, then agent I would like to win the auction, right? So to win, what should he do? He should bid an amount which is larger. Well, definitely, if he bids something larger than the maximum bid, he will bid the bid. So any strategy which is bigger than the maximum bid of the other agent is a best response. So all these strategies is a best response. What about bidding the same amount? It depends, exactly. We don't know. It depends on where I is placed and where the other agents who make the maximum bid are placed in the ordering. It might be a best response or it might not. I don't know. Without knowing what I is and without knowing how the individual bids are, I can't know whether this is a best response or not. So I'll put a question mark there. With the information, I can't do anything. The same thing for this point, the same thing for this point, the same thing for this point. What about for VI? It doesn't matter, it's a straight line. What if the maximum bid made by the other agents is greater than VI? Then he does not want to win the bid. So definitely a strategy bidding less than the maximum bid is a best response. What about bidding the maximum bid made by the other agents? Again, we don't know. It may or may not, depends on the index, the place where I is ordered, and where the maximum bid by the index of the agents who made the maximum bids are placed. So again, I don't know. I'll put a question mark, question mark, question mark. Okay. But you see, when I look at it, even though I don't know whether these points are included or not, what I know is BI is always in the intersection. Okay? So, which implies gamma SPA. So, in a second prize sale bid auction game, I would predict that players, rational players, would bid the value of the object for them if I want to make predictions. If they came and asked my opinion, I would recommend them to bid the maximum, the value of the object for them. Okay? So far, so good? So as a game theorist, this is what I predict. As a game theorist, this is what I prescribe. Any questions? Any questions? Yes, sir.
Okay, which information is missing to know whether the same is the maximum?
So, okay, so which information? Well, it depends. So if I had, for example, let's see, okay, so agent pre-bid 15, 10, 15, 0, well, that's 5, 2. Okay? So in this case, agent 3, 1 wins. There are 2 maximum bidders, 3 and 4. Because 3 on the ordering comes before 4, agent 3 will win the auction. Okay. Yes, so, but if it was this case, okay, then agent 2 would win the auction. So in order to win the auction, agent 3, if the high bidder is player 2, if player 3 wants to win the auction, he should bid more than 15. Bidding 15 will not win the auction for him. But if it was like this, then bidding 15 or anything larger, will player 3 will win the auction. Okay? That's why, I don't know who the other higher bidder. So once I replace the axis with the maximum, some information is lost. The bids of the individual agents are lost. I only know the maximum bid. Because of that, I cannot decide what happens, whether these points are best responses or not. But it doesn't matter. Still, whether these points were included or not, the intersection only contains VI. Okay? Any questions? Any questions? So, it looks like a silly thing to do, the second prize seal bid auction game, the second prize seal bid auction. But one nice thing is one nice property it has is players have a dominant strategy. So that's what they would play, that's what they should play. Okay? The other thing, this is going to be a digression for a while, but many years ago, I forgot, I should have kept a record of that. A government institution, a government firm was privatized by auction. The auction they used was sealed bid. So firms wrote their bids on a paper, sealed it, submitted it to the auctioneer. And the highest bidder won the auction and had to pay what they bid. So that was a first prize seal bid auction game. After the auction was concluded, the winner was determined, and district attorney went to court saying that the auction method was wrong because it was not an open cry auction. Because it was not an open cry, I'll tell you what that means. There was not enough competition, and because of that, the country, the government lost money. So the auction should be canceled. Okay? So what the district attorney was suggesting was, if it was an open cry auction, the revenue to the country would have been more. Okay? Well, let's see. What is that? There are several types of open cry auctions, but so what happens is that the auctioneer starts with a low price, okay? Keeps increasing the price until only one buyer stays in there, only one firm, one individual stays, okay, in the auction. So let's say that we have 4 individuals. The value of the object for player 1, firm 1 is V1. The value of the object for player 2 is V2. For player 3 is V3. For player 4 is V4. If the method of the auction was a second prize seal bid auction, what would happen? Player 1 would bid V1. Player 2 would bid V2. V3, V4. Player 4 would win the auction and pay V3, which seems crazy. Okay. Now let's do an open cry. So we start with a low price. All 4 auctioneers, all 4 players will stay in the auction, right? So I keep increasing, and I went past V1 a little bit. What happens? Player 1 drops out of the auction. He leaves. But I still have 3. So I can keep increasing. Keep increasing. When I pass V2, what happens? Player 2 leaves the auction, drops out. I keep increasing, and when I pass V3, what happens? Player 3 drops out. There's only one player left, so he gets the auction. How much does he pay? V3 or slightly more than V3. So actually, It doesn't matter. The court case was not a reasonable case. Okay, anybody who knew game theory would say that it was not something reasonable. Unfortunately, I don't know what came out of that court. It was not on the news anymore, but it was an interesting case. Okay, we'll do maybe more analysis of auction games and see what game theory tells us about auctions. It's an interesting area of study. Any questions? Any questions? None? Then let's play one more game. So again, please take one piece and pass it around. Can't give these. The game that we're going to play is called Guess 2/3 of the Average game, which is also called Keynes, the economist Keynes, named Beauty Contest Game. The game is as follows. First of all, write your name, an ID number on the paper. What I would like you to do is write an integer from, choose an integer from 1 to So you have to choose an integer, and it has to be an integer between 1 and 99 inclusive. Okay? So what we're going to do is, I'm going to collect your papers. So player 1 wrote x1, player 2 wrote x2, player 3 wrote x3, player n wrote xn. We're going to find the average of these numbers. Let's call it x bar. Okay? And take 2/3 of the average. Among those who wrote the closest to 2/3 of the average, from above or below. The thing is to get as close as possible to 2/3 of the average. Among those, if there's one person, that person will be the winner. If there's more than one person who bid close to 2/3 of the average, I'll choose one of them at random. They will win 3 options, either a book, or a mathematics magazine, or a coffee of their choice from a coffee shop within campus of their choice. Okay? This time I'm serious. I'm not saying I might increase your grade. I might get you coffee. I will get you either a coffee or a book of my choice and a mathematics magazine. Okay? So write a number from 1 to 99, an integer, 1 and 99, inclusive. Write your name and number. Did any one of you play this game before? Okay. So if you did play this before, on the paper, please write, please put a mark, a Y. Yes. The answer is yes. Did you play this game before? So whenever I see a Y, I will understand that you did play this game before. Okay. Again, there's a price. So.
Heard about it, but didn't play.
Well, you don't have to. Well, then put yes again. So, tink, tink, tink. There's a real prize at the end. So the magazine is Matematik Dünyası. It's in Turkish. That's why I make the coffee offer. Those who can't read Turkish can take the coffee offer. And the book is Aha Buldum by Martin Gardner. Those are extra? No, thank you. Sorry? No, but that would not be very fair. I forgot about that. I'll bring it in next lecture, the results. Well, there I said I might increase the grades, but it will not be fair to do so, so it's... Anybody? Well done? Okay, well, let's, again, to start with, we have to model the game. I'm not going to go into details, so how many players there are, I don't know, a number of series, around 60. So the strategy set is this set, okay? Their payoffs, I'm not going to write it, but an exercise, try to do it. So let's see what would happen? Okay. So the first thing I would look for is there any dominant strategies? Okay. For that, you can find best responses, but it's a bit complicated. So rather than looking at best responses, let's try to see if there is any dominant strategies. The first thing that we should notice is that if everybody bids 99, the average would be 99. So 2/3 of 99 is 66, right? So no matter how individuals bid, 2/3 of the average will always be less than or equal to 66, right? So, well, what does that mean? Well,
if you bid it higher than 66, then there's no way you're winning.
If you bid more than 66, there's no way that you're winning. But we can even say more than that, which is writing 66 dominates anything which is bigger than 66, right? 66 dominates 67. So I'm always better off writing 66 than writing 67 or 68 and so on, okay? So 66 dominates any of my strategies which is bigger than 66, okay? So far so good? So far so good? Actually, I was going to do something else. Okay. So I should not write a number bigger than 66.